Managing application state is crucial for ensuring consistency, performance, and user-friendliness in modern web and mobile applications. This comprehensive review examines the most effective application state management (ASM) techniques, categorized into three primary categories: local state management libraries, and server-side state management. ASM involves managing data and user interactions throughout an application's lifecycle, defining the stages of initialization, execution, and termination. It streamlines an application's data and mutations, making the data predictable at various stages of the lifecycle. This predictability enables all parts of an application to access this data when required, presenting it to the user and ensuring consistency and responsiveness. The study analyzes popular front-end frameworks, delving into local state management mechanisms. It evaluates the state of front-end management libraries, highlighting their implementations, benefits, and limitations. Server-side state management techniques, particularly caching, are discussed for their roles in enhancing data retrieval efficiency. The review aims to provide actionable insights for developers to build scalable, responsive applications, bridging the gap between theoretical knowledge and practical application. The study's critical analysis and recommendations guide future research and development in ASM, contributing to the advancement of modern application architecture. The authors categorize ASM techniques into three primary categories. Local state management involves managing state within the application itself, using techniques such as React State Management. State management libraries, such as Redux and Mobex, provide a centralized store for managing state. Server-side state management involves managing state on the server side, using techniques such as caching to enhance data retrieval efficiency. The review highlights the importance of ASM in modern web and mobile application development, emphasizing its role in ensuring consistency, performance, and user-friendliness. The authors provide a comprehensive overview of the current state of ASM, discussing the benefits and limitations of various techniques and libraries. The study's findings and recommendations aim to guide developers in selecting the most effective ASM techniques for their applications, ultimately contributing to the advancement of modern application architecture. Notably, the study's scope is limited to a comprehensive review of existing ASM techniques and libraries, with future work aimed at exploring new techniques and evaluating their effectiveness in real-world applications. The study's assumptions include the importance of ASM in modern web and mobile application development and the need for a comprehensive review of existing techniques and libraries. The single responsibility principle, introduced by Robert Martin in 1972, is a fundamental design pattern for web and mobile applications. It states that software components should have only one reason to change, resulting in scalable and maintainable user interfaces and application programming interfaces. This principle ensures each component carries out one responsibility, making it essential for modern applications. Application state management enables the creation of software components that display and react to small amounts of information within the grand scheme of entire application data. This provides opportunities for client-side and server-side state management, making application architecture robust and cohesive. This comprehensive review categorizes application state management techniques into three categories: local state management libraries, and server-side state management. Local state management is explored in popular UI development frameworks such as React, Angular, and Vue, using techniques like useState, component properties, and data properties. Modern state management libraries, including Redux, Mobex, NGRX, NGXs, Vuex, Recoil, and ZooStand, are analyzed, followed by an examination of server-side state management techniques like View State, Session State, and Application State. The paper provides a critical analysis of the effectiveness, adoption, and future scope of these ASM techniques, recommending key use cases, benefits, and disadvantages of each. The methodology includes an extensive literature review, recent trend surveys, thought leadership pieces, and expert opinions. Typical use cases for each option are documented, resulting in practical and forward-looking recommendations for ASM techniques. The evaluation focuses on React, Angular, and Vue frameworks, as they are leading frameworks used for building modern application UIs. This comprehensive review provides actionable insights for building scalable, user-friendly, and responsive web and mobile applications. In the realm of server-side application state management, ASM, databases play a pivotal role, with Redis and Memcached being prominent examples. As highlighted in the 2023 Stack Overflow survey, Redis has emerged as a leading storage database for caching. Traditional databases, such as SQL, and key-value pair databases are also explored for their ASM capabilities. The study delves into server-side ASM technologies, including the Blazor server, to facilitate efficient state management. Insights from experienced developers and architects, specializing in user interface, backend, APIs, and databases, were collected to provide a comprehensive understanding of various ASM tools and frameworks. Their experiences, including successes and failures, offer valuable opinions on the focus areas of each tool. Market adoption trends are also analyzed through key statistics, such as downloads on popular package managers and stars and forks on GitHub. Local state management, crucial for handling component-specific data, relies on a single source of truth, typically a state container or global state management system. In contrast, server-side state management necessitates effective application state handling to ensure optimal performance and scalability. The paper discusses various server-side technologies and frameworks that facilitate efficient state management, including the Blazor server. Challenges associated with managing state in distributed systems are also addressed, with potential solutions proposed to mitigate these issues. Ultimately, the paper provides a comprehensive overview of the current state-of-the-art in server-side application state management, highlighting the critical role of databases and server-side technologies in this context. Local state management is a critical aspect of application development, enabling the storage and manipulation of data within a specific component or section of the application, without propagating it to other parts. This approach improves performance by limiting data sharing and reducing unnecessary computations. In form handling, local state management facilitates the capture and validation of user input data, such as first name, last name, email ID, and password, storing it locally and submitting it to the server when necessary. This approach eliminates the need to pass sensitive data around the application, reducing the risk of data exposure and improving security. Another use case is presentation logic change, where a component has all the necessary information to display to the user and offers multiple ways to view the data. Local state management enables the component to capture the user's preferences and adjust the presentation logic accordingly, without relying on external state management systems. By managing state locally, applications can reduce the complexity of data management and improve responsiveness. This approach also enables faster development and debugging, as developers can focus on individual components without worrying about the global state of the application. Key benefits of local state management include improved performance, enhanced security, and reduced complexity. By adopting this approach, developers can build more efficient, scalable, and maintainable applications that provide a better user experience. In the realm of front-end development, two popular frameworks, React and Angular, have been utilized to implement a file upload component. This summary delves into the technical details and methodologies employed in both examples. The React example introduces a file upload component as a functional component leveraging hooks. It utilizes useState to manage local state variables for the file and upload progress. The handle file change function updates the file state with the selected file, whereas the handle upload function initiates an asynchronous request to an API endpoint for uploading the file. This function also tracks the upload progress by listening to the onUpload progress event of the fetch API, updating the upload progress state accordingly. The component's return statement includes an input for file selection, a button to trigger the upload, and a paragraph that displays the upload progress when it is greater than 0. On the other hand, the Angular example demonstrates components as JavaScript classes, allowing for the declaration of state variables directly within the class code. State variables can be initialized during declaration, in the constructor method, or in the ng-on-init lifecycle method provided by the Angular framework. The code snippet exemplifies the same file upload mechanism as the React example but with Angular's syntax and lifecycle hooks. A local state variable named upload progress is created to track the file upload status in percentage. This variable is initialized to 0 at declaration and updated in the ng-on-init method. Here is the refined text. In the Angular file upload component, the "handle upload" method is defined to asynchronously handle file uploads. This method utilizes the "on upload progress" callback function to update the "upload progress" state variable with the current upload progress percentage. When a file is selected, the "handle file change" method captures the file and assigns it to the component's "file" property. Subsequently, the "handle upload" method creates a new "form data" object, appends the selected file, and sends a POST request to a designated API endpoint. As the file upload progresses, the "on upload progress" callback function updates the "upload progress" state variable in real time, reflecting the current percentage of upload completion. Upon successful completion of the upload process, the server's response is logged to the console. Conversely, if an error occurs during the upload process, it is also logged to the console. In the accompanying HTML template, an "input" element of type file is present, which triggers the "handle file change" method when a file is selected, thereby initiating the upload process. Key aspects of this implementation include the use of a callback function to monitor upload progress and the incorporation of error handling to address potential upload issues. By asynchronously handling file uploads, this Angular component facilitates efficient and user-friendly file transfer. In Vue, components are JavaScript classes that enable the creation of class variables, serving as local state variables. These variables can be mutated via callback methods, allowing for dynamic updates. The demonstration of local state management is provided through the example of file upload functionality, where the data method is utilized to define initial state variables and data properties, rendering them reactive. The upload progress local state variable is defined within the data method and initialized to a value of 0. Upon receiving details from the onUpload progress callback, the value of upload progress is updated, triggering an update in the view on the user interface. This change is reflected on the user interface through the progress bar. The code snippet illustrates this concept, showcasing the definition of the upload progress variable within the data method and its subsequent update within the handle upload method. The template section of the code defines the user interface, including an input field for file selection, a button for initiating the upload process, and a progress bar that displays the upload progress. The script section defines the component's logic, including the data method, which initializes the upload progress variable, and the handle upload method, which updates the upload progress variable based on the onUpload progress callback. The handle upload method is an asynchronous function that creates a new form data object, appends the selected file to it, and sends a POST request to the API endpoint. The onUpload progress callback is used to update the upload progress variable, which in turn updates the progress bar on the user interface. The reactive nature of the upload progress variable ensures that the user interface is updated in real time, providing a seamless user experience. The update of the upload progress variable is based on the progress event received from the onUpload progress callback, which calculates the progress percentage reflected in the user interface through the progress bar. This approach to local state management may introduce complexity and potential issues with scalability, and future work may involve exploring alternative approaches, such as using external libraries or frameworks, or investigating the application of this approach to more complex scenarios. In the realm of modern user interface frameworks, local state management is a technique employed to efficiently handle data that does not require sharing across various components of an application. Frameworks such as React, Angular, and Vue each have their own implementation of local state management. For instance, React utilizes state variables in class components and hooks in functional components. Angular leverages class properties with multiple options for initialization. And Vue employs a special method data to implement and return local state variables. However, if not used correctly, this can lead to tight coupling between different parts of the application, as too much data needs to be passed around between components, making them interdependent. On the other hand, state management libraries enable the efficient use of data that needs to be shared across multiple parts of the application. This data must remain consistent when accessed in different sections, necessitating a robust mechanism for reliably updating the data. A prime example use case for global state management is in an e-commerce application where information about items added to a cart must stay consistent throughout the application, including the cart page, checkout page, item description page, or any other page. Changes to the quantity of items can be edited at multiple parts, components, in the application and should get reflected in all other places referring to the data. The paper also underscores that local state management techniques are tied to individual frameworks, making it challenging to create interoperability between different applications. It emphasizes the importance of understanding the strengths and limitations of each framework's state management approach to optimize application performance and maintainability. State management libraries facilitate cross-component communication, enabling data sharing between components with parent-child or sibling relationships. This is particularly useful in dynamic scenarios, such as insurance applications where users adjust coverage amounts, deductibles, and addresses to find the best rate. State management libraries enable the active passing of this information to the component calculating insurance premium rates. Another important use case is implementing undo and redo functionality, where users can revert or cancel previous actions, such as in education applications where students can undo and redo specific steps in a math problem solution. The paper focuses on state management libraries for React, Angular, and Vue, highlighting their differences. React has multiple libraries, including Redux, Recoil, ZooStand, and Mobex, whereas Angular has NGRX, and Vue has Vuex. Redux, a popular state management library for React, employs a single data source, the store, which is shared across the entire application, making it a single source of truth. The data in the store is immutable, and when changes are warranted, a new copy of the store data is created through reducer functions, which update the data based on events called actions. Actions are plain JavaScript objects that describe what happened and how the store data should be updated. When an action is dispatched, the reducer function takes the current state and the action as arguments and returns a new state. Optionally, Redux allows middleware functions to perform extra work, referred to as side effects, such as calling an API to load data into the store. For instance, Redux can be used to implement a simple account management part in a banking or financial application, demonstrating viewing balance and actions such as incrementing and decrementing balances. This is achieved by defining actions for incrementing and decrementing the balance, which are acted upon by the balance reducer, and finally, the reducer is taken as an argument when creating the store. Redux's single data source and immutable data approach enable predictable and efficient state management, making it a popular choice for complex applications. By using Redux, developers can simplify state management, improve code maintainability, and enhance overall application performance. In Redux, a popular state management library for React applications, a reducer function is implemented to manage the application state. The "balance reducer" function takes two arguments: "state" and "action". The "state" argument has an initial value of "balance" 0, representing the initial application state. The "action" argument is an object containing a "type" property and a "payload" property. The "type" property can take two values: "increment" and "decrement", corresponding to incrementing and decrementing the balance, respectively. The "payload" property specifies the amount to be incremented or decremented. The "balance reducer" function uses a switch statement to handle the different action types. When the type is "increment", the function returns a new state object with the updated balance by adding the "payload" to the current balance. Conversely, when the type is "decrement", the function returns a new state object with the updated balance by subtracting the "payload" from the current balance. If the type is neither "increment" nor "decrement", the function returns the original state. The store is created using the create store function from Redux, passing the balance reducer as an argument. The resulting store object is then exported, providing a centralized state management system for the application. In contrast, Recoil, another popular library for state management in React applications, adopts a more fine-grained and flexible approach. Recoil breaks down application data into smaller units, enabling a more modular and scalable state management strategy. In the Recoil library, atoms serve as the fundamental units of state management, similar to individual atoms compared to a single source for the entire data in Redux. These atoms can be independently read and updated by components, with only those components subscribed to an atom being re-rendered upon its update. Selectors, special functions in the Recoil library, allow access to an atom's data, the state, and handle side effects such as calling APIs. They also enable the creation of derived states for complex data logic. The provided code snippet demonstrates a basic outline for implementing a feature similar to a banking system using Recoil. A balance state atom is defined with an initial balance of 0, which is then used to create a balance selector. Unlike Redux, there is no need for creating an application-wide data store. Instead, individual components of the React application can access and modify data inside this atom using the use-recoil state hook provided by the Recoil library. In the state.js file, necessary functions from the Recoil library are imported, including atom and selector. It defines the balance state atom with a default value of 0 and exports it. Additionally, it defines a balance selector that retrieves the current balance from the balance state atom. In the banking app.js file, React and necessary functions from the Recoil library are imported, including recoil root, use recoil state, and use recoil value. It also imports the balance state from the state.js file. This setup allows components within the React application to utilize Recoil's state management capabilities without the need for a centralized store. Implementing a banking application using ZooStand, a library for managing global state in React applications, simplifies the API and reduces boilerplate code compared to other state management libraries like Redux and Recoil. A simple banking app example demonstrates the creation of a store using ZooStand's Create API, with an initial state set at 0 and function definitions for incrementing and decrementing the balance. The code snippet illustrates the creation of a store with ZooStand's Create API, defining an initial state and functions for updating the balance. The banking app component subscribes to the state value and methods using the created use store hook, showcasing ZooStand's ability to create a single store that can be sliced and consumed inside React components. ZooStand's core features include ease of implementation, support for middleware integrations to handle side effects, and the ability to create a single store that can be easily consumed by React components. This approach offers a more streamlined state management solution compared to Redux and Recoil, which often require more boilerplate code and complex setup. In comparison to previous state management libraries, ZooStand's unique aspects include its simplicity and flexibility in managing state data flow within a React application. By leveraging ZooStand's Create API and use store hook, developers can efficiently manage global state and reduce the complexity of their React applications. Key benefits of using ZooStand include reduced boilerplate code, simplified API, and ease of implementation, making it an attractive solution for managing state in React applications. By understanding ZooStand's core features and unique aspects, developers can effectively leverage this library to streamline their state management workflow. In the context of state management in React applications, Mobex has emerged as a popular library due to its robust and flexible approach, leveraging reactive programming and decorators to minimize boilerplate code. By breaking down the entire state into small observables, Mobex enables easy consumption of state data via subscriptions, while state modifications are achieved through actions initiated by individual components. Mobex's reactive programming paradigm is well suited for handling asynchronous data streams and event handling. The library provides functions called reactions, which play a crucial role in the state management process. A key implementation aspect of Mobex is the creation of a store using the "create" function, which returns an object containing the initial state and methods to update the state. In a React application, the use-store hook can be created using the create function, as demonstrated in the provided code snippets. This hook is utilized to retrieve the current state and methods to update the state, such as increment balance and decrement balance. Event handlers, like handle increment and handle decrement trigger these state updates, which in turn cause the component to re-render, ensuring the user interface remains synchronized with the application state. The banking app component exemplifies Mobex's reactive programming approach, where state updates trigger automatic re-renders of the component. The component's rendering is conditional upon the state, with the balance being displayed and updated accordingly. The handle increment and handle decrement functions are bound to button-click events, resulting in the state being updated upon user interaction. This approach ensures that the user interface remains synchronized with the application's state, highlighting Mobex's effectiveness in state management. In the realm of reactive systems, managing side effects is paramount, particularly when dealing with asynchronous activities. To tackle this challenge, the concept of reactions emerges as a solution. These are functions that automatically execute whenever the observable state they depend on undergoes a change. An example implementation using Mobex, a widely used reactive state management library, is presented. This example demonstrates the creation of a store class responsible for managing the balance of a bank account. The store class is constructed utilizing the make auto observable API from Mobex, which automatically makes the class observable. An instance of the store class is then created and exported. A new component is also created using the observer API from Mobex, granting the component access to the value of the balance, as well as methods to increment and decrement the balance. The component is defined as a functional component, leveraging the observer higher order component from Mobex. The code snippet provided illustrates the implementation of the store class and the component. The store class features a balance property initialized to 0, along with two methods increment and decrement that update the balance. The component utilizes the observer API to observe the store instance and render the balance value. The authors emphasize the utilization of Mobex's make auto observable API to create an observable store class, and the observer API to create a component that reacts to changes in the store. This approach facilitates efficient management of side effects and asynchronous activities in reactive systems. The example builds upon previous discussions of reactive state management frameworks, illustrating how Mobex can be employed to implement a simple banking application. The authors assume a basic understanding of reactive programming concepts and Mobex APIs. The page does not delve into limitations or future work, instead focusing on providing a concrete example of using Mobex for reactive state management. The authors aim to demonstrate the efficacy of Mobex in managing side effects and asynchronous activities in reactive systems. In an Angular-based application, implementing an NGRX store facilitates state management through actions and reducers. This code snippet defines actions for incrementing and decrementing a balance, which are then used to create a balance reducer that holds the logic for the initial balance as well. The use of selectors allows for efficient data retrieval from the store. NGRX combines the power of RxJS, a library used to implement reactive programming in JavaScript, with the principles of Redux architecture. This framework facilitates state management in Angular applications by maintaining a single, immutable store for data across the entire application. It offers a clean way to manage side effects and integrates directly with Angular Router, enabling routing between pages in the application. Furthermore, NGRX boasts robust developer tooling for efficient development. The example given demonstrates how to create a basic banking app using NGRX, where clicking on buttons triggers actions that update the balance in the store. This showcases the simplicity and efficiency of managing state changes through actions and reducers in an Angular application. In the app module, the Angular component has access to the store, which is initiated within the app module. The store is created to consume the state. Balance. Actions. TS file defines two actions. Increment balance and decrement balance. These actions are created using the create action function, taking a string and a props object as arguments. The props object specifies the amount property, which is a number. The balance. Reducer. TS file defines the balance reducer using the create reducer function. The initial state of the reducer is an object with a single property balance initialized to 0. The reducer handles two actions. Increment balance and decrement balance. When the increment balance action is triggered, the reducer updates the state by adding the amount to the current balance. Similarly, when the decrement balance action is triggered, the reducer updates the state by subtracting the amount from the current balance. The balance. Selectors. TS file defines two selectors. Select balance state and select balance. The select balance state selector is created using the create feature selector function, taking the feature name balance as an argument. This selector returns the entire balance state object. The select balance selector is created using the create selector function, taking the select balance state selector as an argument. This selector returns the balance property from the balance state object. State management is a crucial aspect of modern web application development, particularly in complex applications built with frameworks like Angular and Vue. Two popular state management libraries, NGRX for Angular and Vuex for Vue, leverage concepts from Redux and reactive programming to manage application state in an immutable manner. In the context of Angular, NGRX is used to manage state through a combination of actions and reducers, ensuring immutability. A typical implementation involves importing necessary modules, including browser module and store module, which is configured with a reducer function. This setup enables the application to handle state changes predictably, maintaining a single source of truth for the application state. For instance, an example implementation demonstrates how to manage a balance increase and decrease functionality for a banking system using NGRX. Similarly, Vuex is used in Vue applications to manage state in an immutable way, relying on Redux principles and reactive programming. Vuex provides mechanisms for handling side effects and integrates well with the Vue ecosystem. An example implementation showcases how to implement the same balance increase and decrease functionality using Vuex, highlighting its structured approach to handling data flows and changes within the application. Both NGRX and Vuex offer robust solutions for managing complex application states, promoting predictable behavior and making it easier to debug and test the application. By maintaining a single source of truth for the application state, these libraries simplify the development process and improve overall application maintainability. The paper implements a novel state management store using Vuex's store API, initialized with a balance variable set to 0. Mutations define the logic for increasing and decreasing the balance, while actions commit changes to the store via these mutations. Getters enable components to access store values, demonstrated in the provided code snippet. The Vuex store features increment and decrement mutations for the balance, utilized by actions to modify the store's state. Getters are defined to retrieve the current balance from the store. In contrast, Redux's store is immutable, facilitating seamless debugging and tracking of past actions and states. However, establishing a Redux store requires substantial boilerplate code, which can be mitigated using third-party utilities like Redux Toolkit. Redux's unopinionated approach allows for diverse store implementations, even within the same organization, potentially leading to code maintenance overhead. This flexibility comes at the cost of increased complexity, as different teams may adopt distinct approaches to store management. In the realm of state management libraries for React applications, several contenders stand out. Redux, despite requiring support from third-party tools for developer tooling and middleware, remains a popular choice due to its battle-tested track record and strong community support. It leads in NPM downloads among other libraries. Zustand has gained popularity with its minimal boilerplate code and simple API, making it easy to implement and providing performance benefits by updating only parts of the application that depend on a specific slice of state. It integrates well with React hooks, aligning with the recommended approach of functional component development. Recoil excels in scenarios requiring fine-grained control over state. It breaks down state into smaller atoms, allowing for independent management of each piece of state. Selectors enable seamless side effect handling and creation of derived state. Recoil also uses a hook-based API for integration with React and offers robust developer tooling for development and debugging. Mobex, which has quickly gained fame within the React ecosystem, brings principles of reactive programming. Its decorator-based implementation results in low boilerplate code for initial setup. Reactive programming allows it to scale seamlessly as the application grows. Mobex offers dev tools for debugging and tracking state changes, facilitating development experiments. However, developers may face a steep learning curve due to the additional learnings and complexity involved in reactive programming. Lastly, NGRX is a go-to solution for state management in Angular applications. It utilizes principles similar to Redux, such as immutable state, reducers, and actions. It integrates strongly with the Angular framework and provides robust developer tooling. NGRX uses RxJS for reactive programming, making it suitable for handling asynchronous operations. It also offers built-in side effect handling. Server-side state management techniques are crucial for enhancing application performance and consistency. These methodologies ensure end-to-end application consistency, synchronization between client and server-side states, improved latency, better user experience, and resiliency. Key use cases include form data preservation, user authentication, and e-commerce shopping cart management. In form data preservation, server-side state management ensures that user input in multi-step forms is not lost when navigating between different steps or upon page refresh. For user authentication, it stores a user's login credentials and session token to maintain their logged-in status across various pages. In e-commerce applications, it maintains a consistent view of the items in a user's shopping cart across all pages and components within the application. View state is a server-side state management technique that maintains the state of a web page between postbacks. The scope of this state is limited to a web page and is not shared across pages. This technique facilitates server-side state management, providing an essential tool for developers to manage application state efficiently. By leveraging view state, developers can ensure that user interactions and data are preserved across page reloads and navigation, resulting in improved application performance and user experience. The benefits of server-side state management are multifaceted. It enables developers to manage complex application states, reduce latency, and improve overall application consistency. By adopting these techniques, developers can create more robust and scalable applications that provide a seamless user experience. In the context of Blazor Server, view state management is achieved through sending page content back and forth between HTTP requests. This approach has limitations for large amounts of data due to its inclusion in the HTML page size. For maintaining view state at the server side, another approach offered by Blazor Server involves session state, which stores user-specific data across multiple pages and requests within a session. This state can be stored on a state server, in-memory, or persisted on a data store, depending on persistence and scalability requirements. Session state is effective for storing user authentication information, user preferences, and other session-specific data. Server-side state management is crucial for maintaining the state of an ongoing connection, referred to as a circuit, in applications. The Blazor server provides functionality for maintaining circuit data, which is stored in the server's memory while the connection is active and disposed of when the user navigates away. This approach is useful for storing the state of the UI, field and property values, and data held in dependency injection service instances. However, since circuit data is not persisted in a data store, Sticky sessions are required to ensure that all requests from the same browser are routed to the same server, mitigating state loss. Another mechanism for storing view state, session state, and application state is caching. The selection of technology depends on application requirements. Redis, an in-memory data store, stores data in memory and persists it in a data store, offering high performance. As Redis stores data in memory and persists it in a data store, it is a viable solution for applications requiring both high performance and data persistence. The choice between Blazor server and caching technologies like Redis depends on the need for sticky sessions, data persistence, and performance. While Blazor server is effective for restoring state during temporary network connection losses, it cannot retain circuit data across server restarts or in multi-server deployments. In contrast, Redis provides a high-performance solution for storing and retrieving data, making it suitable for applications requiring both high performance and data persistence. The importance of selecting the appropriate technology for server-side state management is highlighted by the limitations of each approach. Blazor server requires sticky sessions, while caching technologies like Redis may incur performance overhead. Assumptions made in this discussion include the need for high-performance solutions and the importance of data persistence in certain applications. Future work may involve exploring additional technologies and approaches for server-side state management and caching. Server-side state management techniques are crucial for maintaining user-specific data across multiple requests and pages. The view state technique is a straightforward approach that automatically sends state information back and forth between HTTP requests, requiring no server-side configuration. However, its limitations are notable. It is confined to a single web page, cannot be shared across pages, and can substantially increase HTML page size, leading to slower load times and higher bandwidth usage, rendering it unsuitable for large datasets. In contrast, the session state technique offers a more robust solution, storing user-specific data across multiple pages and requests, making it ideal for applications requiring user authentication, personalized content, and shopping cart management. This technique leverages server-side storage, allowing for efficient data retrieval and manipulation. Nevertheless, session state can lead to scalability issues and increased server load, particularly in high-traffic scenarios. Another approach is the application state technique, which stores data shared across all users and sessions. This method is well suited for caching frequently accessed data, reducing database queries, and improving overall application performance. However, it requires careful consideration of data synchronization and concurrency issues to ensure data integrity. Database state management techniques, such as storing data in relational databases or NoSQL data stores, offer a more traditional approach. This method provides a centralized repository for user-specific data, enabling efficient data retrieval and manipulation. However, it can lead to increased database queries, affecting performance, and requires careful database design to ensure data scalability and integrity. In conclusion, each server-side state management technique has its advantages and limitations. Understanding these trade-offs is crucial for selecting the most suitable approach for a given application, ensuring optimal performance, scalability, and user experience. Application state management, ASM, is crucial in modern web and mobile application development, ensuring consistency, performance, and user-friendliness. ASM techniques can be categorized into four main groups: local state management libraries, server-side state management, and local storage solutions. Local state management involves handling component-specific data, with popular frameworks like React, Angular, and Vue providing efficient solutions for use cases such as form handling and presentation logic changes. State management libraries, including Redux, Recoil, ZooStand, Mobex, NGRX, and Vuex, offer robust solutions for managing global state and cross-component communication. Each library has its strengths, with Redux being widely adopted due to its battle-tested nature, and newer libraries like ZooStand and Recoil offering simplified APIs and fine-grained control, respectively. Server-side state management techniques such as view state, session state, and application state play a crucial role in maintaining consistency between client and server, improving latency, and enhancing user experience. Technologies like Blazor Server, caching solutions, Redis, Memcache, and various data stores offer different approaches based on application requirements. The choice of ASM technique depends on the specific needs of the application, considering factors such as scale, performance requirements, and development team expertise. Certain use cases can be achieved at both server-side and client-side, with the decision to use a particular technique depending on security needs and available infrastructure. For example, more sensitive applications dealing with PE data should use server-side ASM, while others may implement ASM using popular client-side techniques. When selecting an ASM technique, two open challenges must be considered. Firstly, balancing the need for powerful state management capabilities with the desire for simpler, more intuitive APIs remains an ongoing challenge. While libraries like Redux offer robust solutions, they often come with a steeper learning curve and more boilerplate code. Secondly, maintaining performance while managing increasingly complex state becomes challenging as applications grow in complexity and size. Optimizing state updates and minimizing unnecessary re-renders are areas that require ongoing attention. Ultimately, the choice of ASM technique depends on the specific needs of the application, and considering the trade-offs between complexity, simplicity, and performance is crucial for effective state management. In the rapidly evolving realm of application state management, ASM, 9 key areas require further development and improvement. Synchronization between client and server is critical, particularly in real-time applications or those with offline capabilities, to ensure seamless state synchronization across both sides. Security concerns are paramount, encompassing both client-side storage and server-side caching mechanisms, to protect sensitive user data. Maintaining consistent state management across web, mobile, and desktop versions of an application is a significant challenge due to cross-platform development. Developing effective testing strategies and debugging tools for state-related issues is also crucial as state management complexity increases. Adapting state management techniques to accommodate emerging paradigms, such as micro front-ends and server components, is necessary. Optimizing state management techniques for edge computing environments, which are distributed and close to the user, presents new challenges and opportunities. Industry adoption should be considered when choosing a particular ASM technology and technique, including community support, market adoption, and implementation complexity. Addressing these challenges is crucial for the continued evolution of ASM, ensuring that developers can build sophisticated applications while maintaining performance, security, and user experience. Ultimately, these challenges must be addressed to ensure the continued growth and sophistication of application state management, enabling developers to build complex applications while maintaining seamless user experiences. ASP.NET offers various state management options, each with distinct implications for developing systems on the Glance project. A standardized architecture is crucial for enhancing system development efficiency and scalability, as emphasized by Carlos Henrique Ferreira Brito Filho, Gabriel José Souza e Silva, Gloria Corti, and Joel Closure in their work. The authors highlight the importance of migrating to a standardized architecture to improve system development. The paper discusses the limitations of traditional state management approaches, including view state, session state, and application state. These methods can lead to increased memory usage, decreased performance, and reduced scalability. In contrast, a standardized architecture utilizing a distributed caching system, such as Redis or Memcached, can provide a more efficient and scalable solution. The authors propose a novel approach to state management, leveraging a combination of caching and a centralized state management system. This approach enables the decoupling of state management from the application logic, allowing for greater flexibility and maintainability. The proposed architecture is designed to support the development of large-scale systems, with a focus on scalability, performance, and reliability. The paper presents a detailed analysis of the proposed architecture, including its components, interactions, and benefits. The authors also discuss the implications of implementing a standardized architecture, including the need for changes to the development process and the potential impact on system performance. Key findings from the paper include the importance of standardizing state management to improve system development efficiency and scalability. The authors also highlight the benefits of using a distributed caching system and a centralized state management system to support large-scale system development. The proposed architecture provides a novel approach to state management, enabling the development of more efficient, scalable, and maintainable systems.